Hello and welcome to my today's presentation. The title of my presentation is Deep Learning Forecasts of the Electricity Price with Special Consideration of the Electricity Supply. My name is Jan-Hendrik Meier. I am Professor of Accounting at University of Applied Sciences in Kiel in Germany, and the paper was written together with my co-authors Stephan, Schneider, Darya, Sizova and Cansu, Tanriver. My presentation is structured as follows. First of all, I would like to introduce into electricity price forecasting and into rigor and relevance. Then I would like to demonstrate some prior research and our research gap. I would like to go into the sample and the methodology. I would like to show some results and the discussion, and I would like to conclude and point out some points for future research. So, a short or brief discussion about the rigor of the methodology. Well, forecast models are of course based on statistical methods. Statistical methods can be differentiated into in-sample tests and out-of-sample tests. In-sample tests are used to gather some statistical inference, so statistical testing. Out-of-sample tests are used to estimate forecasting accuracy. Accordingly, often out-of-sample tests are meant to be unscientific because you won't gather any statistical inference. Due to that, only 2 international journals are focusing on forecasting models. Nevertheless, there is a huge relevance for forecasting, especially for power plant operators, if we speak of electricity prices, for storage power station operators, for electricity suppliers and network operators, and for industrial electricity customers, who all want to know about the future electricity price. Why can we forecast electricity prices? Because electricity is not yet storable. If it was storable, it wouldn't be a problem. Buy the electricity, store it and sell it if the price is high, but that is not possible. So if there are certain seasonal patterns or daily or hourly patterns, they will sustain in the data because you can't store the electricity. This is what we see. We see clearly recognizable patterns, and we do not have any Markov property, so electricity prices are not comparable to stock markets where forecasting would be impossible. And of course, there are interferences between different seasonal patterns. Usually, it is assumed that the supply side of the electricity market follows the demand side to keep the net stable. Accordingly, the power plant operators will supply as much electricity as is needed by the demand. But due to renewable energy and, accordingly, a change in the supply mix, this assumption cannot be held upright. Let me give a brief example. We have wind energy, we have solar energy, and wind energy will emit electricity into the net if the wind is blowing, and solar energy will emit electricity if the sun is shining, and so we need some forecasts to keep the net stable. Here we see the electricity price between 2015 and 2018. What strikes our eyes are spikes going up and down, especially due to time and weather conditions, and what is very interesting, we see negative electricity prices that correlate strongly with wind energy. So if the wind is strong, we see prices even dropping below zero, which means that plant operators need to get rid of their energy because they cannot switch up, for example, a nuclear power plant that will take several days. So they need to get rid of their electricity, and they pay some money to customers who are willing to take the electricity. There's a whole lot of prior research on that, so we found more than 280 articles in the International Journal of Forecasting only on power price or power load forecasting. There's a literature review available from Veron in 2014, but there are only 11 articles that are identified with a special focus on the supply side, not only on meteorological issues. Meteorological issues are mainly everywhere. What is the research gap here? We have highly complex independencies on the supply side behavior of electricity prices, and there is no research on German data so far. So where do these highly complex independencies come from? It's from the supply mix. If the wind is not blowing and the sun is not shining, there is of course a drop in electricity supply. And other more conventional power plants cannot easily be adjusted. So a nuclear power plant cannot be adjusted, a coal power plant cannot be adjusted. Accordingly, gas power plants have to be used, and gas power is extremely expensive for electricity production. So, different mixes of energy will lead to different cost, and of course that will be reflected in the prices. That's the research gap here. So we look at those complex independencies between those supply side mixes. Our sample data, or our data source, is the EEX, the European Electricity Exchange Felix DE day-ahead spot rate between 2015 and 2018. We gathered some 24-hourly price observations a day. And we took supply-side data from ENTSO-E transparency platform in megawatts. And we have a mix of 20 energy types, and that are biomass, lignite, gas produced from coal, gas, hard coal, oil shale, peat, geothermal energy, hydropump storage, run-of-river power plants, water reservoir, marine, nuclear, other, solar, waste, and other renewable energies, as well as wind offshore and wind onshore. Also, we introduced into our models dummies for month, weekday, and hour to cope with seasonal patterns. For the pre-processing of our data, we imputed missing values by spline interpolation, and we differentiated the time series once due to KPSS stationarity tests. Our training and test data subsample is 260 weeks prior the predicted week. That's the training data set, and we predicted 12 randomly chosen weeks in 2017. What's our methodology? Of course, to compare different methods, we need benchmarking models. Our first benchmarking model beneath normal regression, normal OLS regression, is the Arimax 515 model. The Arimax 515 model was found using the Hindman-Kandakar algorithm to find the best notation. Our data is normalized using min-max scaling for neural networks, and we apply, first of all, a single layer perceptron, which should be mainly like an OLS regression, should behave like that. We apply deep learning multi-layer perceptrons with 3 hidden layers made out of 128, 64, and 32 units. A deep learning LSTM, long short-term memory model, again with 3 hidden layers, 128, 64, and 32 units. And of course we apply k-fold cross-validation in the form of a sliding window, which is used to optimize the hyperparameter of the number of epochs. Here are our results for the Arimax model, for the regression, for the single layer perceptron, for the multi-layer perceptron, and for the long short-term memory neural net. And we are not 100% convinced that the more complex models are delivering better results here, although particularly we see several models that are a lot better. In the regression analysis, the variables lignite, gas, hard coal, oil, hydropump storage, water, solar, wind offshore, wind onshore, the months 5 to 8, and all days of the week and all hours are significant predictors for the forecast model. So we see lots of highly significant determinants here. In the overall view of our forecast models, none stands out as dominant, even if MLP and LSTM deliver noticeably better results than the simpler forecasting models. What we see here are differences in seasons, so the winter is much harder to forecast than the summer, which is completely in line with the prior literature. A little outlook on our future work. So with regard to other projects, the following network types will be used by us in the future. We will try to apply temporal convolutional neural networks, so CNNs, with dense layers, with time-distributed CNN layers connected with LSTM layers, and the combination of both. And, which is very new, is neural networks with attention mechanisms. So this is a little outlook on what we plan so far. The main author is my dear friend Stephan Schneider, whose picture you see here, and who will now go into the discussion with you. Thank you for your attention. Bye-bye.